Hello, in this video we are going to study about the subtraction of vectors. Subtraction of vectors basically is the addition of a positive and a negative vector. Now, a vector generally is just a vector, but the negative of any vector is when we consider the vector with the same magnitude but just the opposite direction. So if we are to subtract a vector from the other, we just add the negative of the other vector. Like in case of if I say I have a vector A over here and B over there, and they are separated, or they are making an angle theta with respect to one another, we know that just A plus B in terms of the vector addition is going to give us the magnitude of it is obviously equal to the square of A, the square of B added to 2 times AB cos theta, where 2 times of AB cos theta is theta being the angle between them. Now, if we are to consider the vector A minus B vector, now in that case we can just take it as A vector plus of minus B vector. Now, as you know, the minus B vector will be exactly can be taken in the opposite sense that I am just representing by dashed line along the opposite direction, and exactly the same magnitude goes up until here. So this is the negative B vector, like a negative is minus B. So the minus B vector acts along the opposite direction with the same magnitude, and the angle obviously is 180 minus theta. So in that case what we have is that for obtaining the magnitude of the resultant of A minus B, what we have is A vector minus B vector, the mod of that is the magnitude in that case is equal to A squared plus B squared plus 2AB cos 180 minus theta. Now with this cos 180 minus theta, you have that to be equal to minus cos theta, so you have it as A square plus B square plus, or rather minus 2AB cos theta, because cos 180 minus theta is minus cos theta. So in that case you have this value as the magnitude of A minus B vector. With that being the magnitude of A minus B, we can obtain the direction as well, and as you know, we have a rule for, or we have a formula for obtaining the direction of the vectors, and that being the case where we have it to be equal to let's say the resultant is, suppose I draw it over here, the resultant is along this line like this is the resultant. Let us say this is R dash, giving me the resultant of A minus B. So, and that resultant obviously makes a certain angle, let that be equal to I take it as alpha. Here I take it as alpha, it's overlapping over there, so the angle between A and R dash vector is alpha. So in that case we have tan alpha to be equal to is the same process that we had used in the parallelogram law as well as the triangle law of vector addition. We have V sine 180 minus 180, actually it's for tan case what we had is tan 180, in that case we had theta, here we have 180 minus theta divided by A plus B cos 180 minus theta. Now the sine theta part remains positive for 180 minus theta case, so we have B sine theta over here, but in the denominator we obviously have 180 minus theta in case of cosine is minus 180 minus cos theta. So a minus b cos theta is the angle, is the tangent of the angle that the resultant makes with respect to one of the vectors, in this case being a. So you have the value of alpha to be equal to the tangent inverse of b sine theta divided by a minus b cos theta, and in that case you have the angle. In this case you have the magnitude as a whole. So that's more or less the magnitude and the angle part of it. And then again, considering the case of relative velocity. Now relative velocity, I have a video on relative velocity, but I can explain it once again. The case of relative velocity is that if we are relating the velocity of a moving vehicle with respect to anything else. Now, anything else, the other thing may be a stationary tree that is by the side of the road, or anything. The ground itself is stationary; it isn't moving. And in case of any other vehicle, any moving vehicle that you have along the road as well. So that's more or less how we relate the velocity of one object with respect to other. The velocity in this case is one moving object with respect to other, is what you are comparing. Now suppose you are moving in a vehicle, you are sitting in your car and you observe a tree outside, and as you move up, as you go past that tree, you find it to be moving backward direction, provided you consider yourself to be stationary. Now once you consider yourself to be stationary, what you find is, even if the tree is stuck to the ground over there, but the tree moves past you, and the faster the rate of your vehicle in motion in the forward direction, the faster is the motion of the tree in the backward direction, even if it's stationary. So that gives you an account of how you observe things, or how you relate the motion of one thing with respect to other. In this case, what you are doing is you are considering yourself to be in a stationary frame, and with yourself as stationary, the although you're moving actually, uh, the other things relate to you in a different way than they might actually be. So let's take a mathematical approach to it. Now in that case, what we have is, we just uh, the the usual way of representing or relating one thing to another is that, suppose a vehicle is moving with a speed VA along a road. Now VA being the speed of the vehicle, and obviously the ground is stationary, as I said. There's no velocity associated with the ground, is it? So obviously Vg goes to 0, so Vg is equal to 0 in that case. Now as you have the case of relative velocity, you have Va with respect to g, that is how we read it. That is the velocity of A with respect to the ground in this case. So this is the velocity of A with respect to the ground, and that is written as Va minus Vg. And obviously you know that Vg in this case is 0, so you just have it as Va. That is the speed of the vehicle with respect to the ground. The ground is obviously stationary. Now instead of ground, if you hold yourself over there and you just observe a vehicle moving along the road, and it goes past you with a speed Va, then its relative speed with respect to you, that is Va with respect to you. In that case, you may be anything. So that is absolutely the exact velocity with which it is moving at that point of time. Now if we consider another vehicle, and that other vehicle, now obviously let's take it the other way around. We have the, let's say, the velocity of ground with respect to A. Now again, we are back to the example where you can consider yourself to be stationary while you're sitting in your car and you observe a tree or anything outside. or a spot on the ground maybe. So in that case, what you are taking is as per the formula over there, that is Vg minus Va. But as you know that Vg is simply 0, so we have velocity of ground with respect to the vehicle A moving at a speed Va is simply the opposite way or the other way around, because the vehicle or the person in the vehicle is considering himself to be stationary. What he observes outside is that the ground or the spot on the ground or even the tree, whatever it may be, it's traveling at a speed of Va but in the direction opposite to its direction of motion. Now, you do not consider yourself to be in motion in that place, you just consider yourself to be at rest. You observe that the other thing moves in the backward direction at the same speed. The greater your speed, the greater is the speed of the backward motion of the stationary object. So taking that into account, what we have, we may consider another vehicle. Now in case of another vehicle, let us say VB, which is another vehicle B which is moving with speed VB, what we have is that VB obviously with respect to the ground is simply equal to VB minus VG. Vg obviously goes to 0, so you have all that you have is Vb. Now if we are to calculate Va minus Vb, let's see if we are getting the same thing, a relative velocity, or this is this giving us the relative velocity of A with respect to B? It certainly should, because what we have over here is Va was simply equal to Vag minus what we had Vb is equal to Vbg. Now this is simply rearranged as a Va with respect to G, and this can be taken the other way around. I can take it as plus and Vg with respect to B. Now if you observe this last thing that I have written over there, what we are saying over there is that the velocity of A with respect to B is simply the velocity of A with respect to any third stationary object considered. In this case it is the ground, plus the velocity of the ground with respect to B. Now as you know, the velocity of ground with respect to B will be minus Vb. So that is what we are looking at. So that is giving us a brief idea about the velocity of A with respect to B, because now consider the case where two vehicles, both the vehicles A and B, they are traveling at some other road. Maybe one of them is traveling in one highway and the other one is traveling in some other highway. So how do we relate the speed? They are not in the same line, or they are not along the same direction or something like that. So how do we relate that? Because in case of ground, what we had is that you can see observe the ground. You are observing it to be moving in the backward direction while you consider yourself stationary, but actually you are in motion in the forward direction. But what about two vehicles which are on separate roads, but we still want to obtain the relative cases or relative velocities? So in that case, what we need is that we need a stationary object to which we can compare. We can compare the moon as well, because the moon is stationary. Suppose you are traveling during the night time and you observe the moon is stationary with respect to you, but that doesn't really sound that good. That sounds a bit poetic, but in this case what we have considered is very much a physical thing that we can take into account, that is the ground on which the vehicles are moving. And this is simply the velocity of A with respect to B is that the velocity of A with respect to the ground plus the velocity of ground with respect to B, or the other way around, that is velocity of B with respect to ground, taken in the negative sense. So this set of formula is what is going to help us to determine the relative velocity between objects, or it's simply vector subtraction that we have just studied a few minutes back, right here in this page that you have in front of you. Now, moving back to, or moving forward to the case of relative velocity. In case we can take two examples. We have the rain and man problem. We have the rain and man case. Sorry, I forgot to change the page in this case. We have the rain and man case, where a man holding an umbrella tries to determine how or in what direction must he hold so as to protect himself from rain as he is in motion, so as because it's not the same way when he's at rest, because when he's at rest, if the rain is falling vertically downward, then he will just hold it upward, right up. But if he is moving along the path or along the road while the rain falls vertically downward, then the condition changes a bit, which you might have experienced when you are driving. Let's say a two-wheeler will give you a better experience. In case of a two-wheeler, when you're riding on a bike or something on a rainy day, the rain seems to be uh, hitting you right on your face, obliquely, instead of just falling on your head. If it obviously falls on your head and everywhere, but it hits you more painfully in the eyes or on the face. So that is the case when you are having a certain speed horizontally while the rain is falling vertically. Let's take that case and choose the relative velocity that we have just studied. So rain usually falling in the vertically downward direction, like that. You have Vr, that is the velocity of the rain in the vertical direction. A man is traveling along the horizontal road. This is the velocity of man. But now, what is the velocity of rain with respect to the man? How he observes the rain to be falling onto the ground. Now, because it's the velocity of rain with respect to the man, so we can use the relative velocity case of where Vr minus Vm, and this is simply Vr. As you know, it is plus of minus Vm. Now, as we take plus of minus Vm, I can just use another ink to show you what we are considering over here. What we are considering is that we have the negative direction of the person along this line. Minus Vm lies along that line. And in this case, because you see the red arrowhead over here, so what you can say is that Vr and V minus Vm, they are in the same sense, and we can just use the triangle law where the third closing side is taken in the opposite sense, which gives us the resultant. So the velocity of rain with respect to man in this case is at an angle theta with respect to the vertical. Now, if suppose he was holding his umbrella like this in the upward direction, when the rain was falling like this in the vertically downward direction, now as he is moving along the road horizontally with a speed Vm, he must hold the umbrella, or he has to hold the umbrella like this, so as to protect himself from the rain. So that's more or less the rain and man problem that we come across. We are supposed to determine the angle to which the umbrella must be bent. Obviously, as you can see that these two lines are parallel, so this angle has to be theta, that is the angle with which he observes the rain to be falling onto him. He must bend his umbrella at an angle theta from the vertical. From the horizontal, obviously it is 90 minus theta, but obviously he wasn't holding the umbrella horizontally from the beginning. He was holding it vertically upward. So obviously from the vertical position he has to bend it through an angle theta in order to protect himself as he moves, or as he starts moving at a constant speed of Vm. Now we have another general problem of case where we are supposed to obtain the swimmer stream, boat stream, or something like that, both stream cases. Now in the boat stream case or the swimmer stream case, we can also take it as swimmer. The swimmer is swimming across a stream. We'll be doing a few numericals on this in the numerical section of the vectors. So this is more or less a stream, where the stream has its water flowing along the dashed lines that I'm showing right now along this direction, suppose, where obviously I have a stream, or it is even a river. You can take it as river. So this is the velocity of the river, Vr. And a person, a swimmer, wants to just move, or a boat maybe wants to go from one side to the other side over there, that is from A to B. If he is heading along this line, now this is the line along which he was heading, and he has a certain speed lit, and this is his own speed when this is supposedly a swimmer, and this was his own speed when he with which he can move across a still river or a still water. But obviously, as you know, this river is flowing, and it is flowing with a velocity Vr. So now the person has a resultant speed. You can use the triangle law over there, and from the triangle law of vector addition we have V, and this is the resultant of the swimmer, the velocity of the swimmer and the velocity of the river. So V is simply equal to the vector addition of Vs plus Vr. How does he then approach? This will be at a certain angle, obviously, with respect to his line of approach for swimming. Then how must he approach so as to reach exactly at the point B? Now in order to do that, what he must do is he must start like this. Now if he starts at a certain angle right from the very beginning, this is Vs, of course. This is the first case. Let me consider the second case in the next diagram. This will be a bit clumsy over here if I draw it, so I'm just cancelling that. Okay, spare me for that mess, but we are considering that diagram again. So here is the stream that is flowing along the right hand side direction of yours. This is the velocity of the stream, maybe the river, and the swimmer just wants to move from the point A to the point B exactly on the opposite side. So what does he do? He must start at a certain angle, and we usually have to determine that angle. So if he is to reach over here, so the swimmer must start here such that the velocity of the river pushes him along this direction, and finally he ends up along this line. So here again we have V to be equal to Vs plus Vr. But as you can see, the angle is an obtuse angle in this case, so that is to be obtained. Now how do we obtain that? You obviously have a right angled triangles over here, so that won't be a big problem. Let this be theta, This is obviously 90 degrees, so this is just 90 plus theta, the angle over here with respect to the horizontal. With respect to the vertical, he must start at an angle theta. So these angles can be determined by considering the dimensions or the velocities over there, or even the dimensions that might have been given in case of the width of the river or anything like that. Now, if you observe, what we have in this case is that the final velocity in case of in the second case, let me name them. This is the first case and this is the second case. Now, in the first case, what you find is that the final velocity will obviously be greater because it's a vector addition, and the vectors are at right angles to one another. So here what you find is v has the magnitude of just vs squared plus vr squared under root, which is obviously greater than both individually both of them. But in this case, in the second case, what you find is that v will be something less than vs. Obviously the swimmer here is moving upstream. Now what do you mean by the term upstream? Upstream means he has to struggle against the waves, because the waves are, or the river is flowing along this direction that I've just indicated by the arrow towards the right hand side, while he is taking fractionally left direction. So obviously he has to struggle against the river. So this v that you are getting is obviously less in magnitude than vs, while this v that you are getting is greater than vs. So that means that here in the first case the time taken will be less because the velocity increases, means he will cover the distance in a short time. But here what you have is that the distance covered is less, or the displacement is, or the distance covered is displacement is considered or taken into account. So all that you have in this case is displacement in the second case, while in the first case you have the least time. So the least time case is the case where he is heading off exactly across the bank or across the river, while the least possible distance is when he has to move upstream. When he starts upstream is the time when he ends up with the least distance. So we can, or you can try a few examples, or we will obviously deal with the numericals associated with this topic in the numerical section of the vectors, but that is in the upcoming videos. We'll be discussing many more about component of vectors, as well as the uh, vector multiplication, but that is in the following videos to follow. Till next time, thank you.